Now, because enantiomers are technically, three-dimensionally, and actually different from each other, we have to have some way of naming them to distinguish one enantiomer from another. We do this by using a system called the Cahn-Ingold-Prelog Hanna-Barbera Yabba-Dabba-Doo system, which I just sometimes call the RS naming system for short. How does the RS naming system work? I'll give you some steps. Step 1, find your stereocenter atom. Step 2, prioritize the 4 different substituents coming off of the stereocenter atom. Now, how in the world do you prioritize them? Well, what you do is you start at your stereocenter and you go out one atom at a time. Highest priority equals the atom that has the highest atomic number. Now, if there's a tie, then you go out one more atom, and so forth and so on until you break the tie. Now, one thing I hasten to mention is this. Isotope atoms have the same atomic number. So if I have 2 isotope atoms of each other, which one gets higher priority? Well, as it turns out, the one that gets higher priority is the isotope that has the higher atomic weight. So once you've done step 2, you now move to step 3 by numbering your substituents 1, 2, 3, and 4 from highest to lowest priority. In step 4, you have to three-dimensionally point the lowest priority substituent, that is priority group number 4, away from you. Now, for people who are new at this, it's often very helpful for you to build a three-dimensional model so that you can hold it in your hands and see. Step 5, make a circle going from substituent 1 to 2 to 3. If that circle ends up being clockwise, then that is an R stereocenter. If it ends up being counterclockwise, then it is an S stereocenter. Now, one way you can remember that is by looking at this figure. If you were holding a steering wheel while driving a car and you wanted to turn right, you would turn it clockwise, wouldn't you? Thus, we can remember that clockwise is R, because if I were holding a steering wheel and turning clockwise, my car would turn right, which begins with the letter R. Now, if I were holding a steering wheel and turning it left in a car, that would be counterclockwise. So I can remember that if I'm holding a steering wheel and I'm going counterclockwise, it is left, which corresponds to S. So I sometimes tell students to remember right or clockwise corresponds to R, and sleft or counterclockwise corresponds to S. R for right and S for sleft. Yeah. So let's go ahead and give this a try. Starting with this lecture problem, I want you to assign R or S configuration to the following molecule. Step 1, we find our stereocenter. You'll note that there's only one carbon atom in this whole molecule that is bonded to 4 different things, and it is located right there. In step 2, I'm going to prioritize all of the atoms that are bonded to that stereocenter. You'll notice that this carbon is bonded to a bromine, a chlorine, a hydrogen, and a carbon. Which of those atoms has the highest atomic number, and therefore the highest priority? Of course, the answer is bromine, so it gets priority number 1. Which has the second highest atomic number, and hence the second highest priority? That would be chlorine. What has the third highest? Carbon. And the fourth highest? Hydrogen. In step 3, I now draw a circle going from substituent 1 to 2 to 3. You'll note as you look at this that going from 1 to 2 to 3 is counterclockwise. We remember that if I were turning a wheel counterclockwise in a car, I would turn my car left, or sleft. Thus, this stereocenter is an S stereocenter. Let's now look at this one. Same type of question. Assign R or S to the configuration to the following molecule. You'll notice that there's only one stereocenter in this molecule. It's this carbon atom located right there. This carbon atom is bonded to a bromine, a carbon, and a hydrogen. Who has the highest atomic number and hence the highest priority? The bromine. Hence, he is number 1.
Ramses is the number 1. His legs are number 1.
Now, what I have left is a carbon, and a hydrogen. The hydrogen is obviously and always going to have the lowest atomic number when we do this, so it will be 4. But what about this carbon and this carbon? Who wins? Well, they have the same atomic number. So I have to go out one more atom until I break the tie. This carbon is bonded to two hydrogens, which I'll just ignore, and it's bonded to another carbon. This carbon up top is also bonded to another carbon. Which atom has a higher atomic number and hence a higher priority? This carbon here or this carbon there? Of course, they once again tie. So I have to go out one more atom. This carbon is stuck to two hydrogens that I'll ignore, and it's also stuck to another carbon. The carbon up top is stuck to two hydrogens, which I'll also ignore, and it's stuck to a bromine. Have I broken the tie? Yes. Thus, the branch up top has higher priority than the branch down bottom with relation to this stereocenter in the middle. Hydrogen is, of course, the loser, having the lowest priority number of 4. What do I do now? Well, now I trace a circle going from 1 to 2 to 3, which I'm doing with my pointer right now. And I ask myself, is this circle going clockwise or counterclockwise? You'll note going from 1 to 2 to 3, I'm going clockwise. Clockwise, with a car wheel, would turn my car right. Hence, this is an R stereocenter. Let's see if we can do this one. My stereocenter is located here. It's stuck to a carbon, a carbon, a carbon, and a hydrogen. Obviously, the hydrogen is going to have the lowest priority. But who gets the highest priority of these 3 carbons? In order to figure that out, I have to break the tie. You'll note that this carbon over here to the right is only bonded to hydrogens. Hence, he is going to be the loser among these 3 carbonated appendages. This carbon over here is single bonded to another carbon, while this carbon up here is double bonded to another carbon. For priority's sake, that's kind of like saying this carbon is bonded to 2 carbons, while this carbon is only bonded to 1. Thus, the appendage up top gets priority number 1. This ethyl group over here to the left gets priority number 2. The methyl gets priority number 3, and the hydrogen gets priority number 4. Now you'll note, an earlier step that I skipped for our last 2 examples says that you have to point the lowest priority substituent 3-dimensionally away from you when you're determining if something is R or S. This hydrogen is actually pointing 3-dimensionally towards us, so that could create a problem. Let me go ahead and draw my circle. Going from 1 to 2 to 3, as written here, it looks like it's going counterclockwise. However, if I were sitting on the opposite side of this screen, that is, if I were back here looking 3-dimensionally towards this carbon, so that this hydrogen were pointing 3-dimensionally away from me, which is what is required, then this circle going from 1 to 2 to 3 would indeed be clockwise, not counterclockwise. Thus, this is an R stereocenter. So once again, this example illustrates the fact that you have to point the lowest priority substituent 3-dimensionally away from you. Now, if you have difficulty seeing that, please don't hesitate to build a 3-dimensional model. Here's another example, which I'm not going to do for you, but will let you attempt to do on your own. So this brings us to another series of questions. Are the following pairs of molecules pairs of enantiomers? Can we do this? Well, the best way to do it is one at a time to assign each stereocenter in each molecule as being R or S. Let's begin by looking at this molecule over here. My stereocenter is located right here in the middle. It's bonded to a bromine, a carbon, a hydrogen, and a carbon. Which of those has the highest atomic number and hence the highest priority? The bromine does. Now between these 2 carbons, they obviously tie, so I have to go out until I break the tie. Carbon at left is bonded to a hydrogen, carbon at right to an oxygen. Thus the carbon bonded to the oxygen is higher priority and gets priority number 2, while the carbon to the left becomes priority number 3. The hydrogen, of course, is the loser at group number 4. I trace my circle, 1, 2, 3. It looks like it's clockwise, but my lowest priority substituent is pointing 3-dimensionally towards me. Thus, if I were actually on the opposite side of the screen staring at it, this circle would indeed be going counterclockwise, which is S. Let's do the same for the molecule shown here to the right. Bromine is highest priority, followed by this group to the left, followed by the methyl to the right, followed by the hydrogen. Tracing my circle 1 to 2 to 3, it looks like it goes counterclockwise. However, because priority group number 4 is pointing 3-dimensionally out of the screen towards us, this ends up actually being clockwise. That is, if I were physically standing behind the screen and staring at this molecule so that the hydrogen were pointing away from me, going from 1 to 2 to 3 would be clockwise. Hence, this is an R stereocenter. Let's shift over here to the molecule all the way to the right. My stereocenter is in the middle. It's bonded to an oxygen, hydrogen, carbon, and carbon. Who's the highest priority? Oxygen. Who's higher priority between these two groups once I break the tie? The answer is the guy up top, who gets priority number 2. Guy at the bottom is priority number 3, and the hydrogen is priority number 4. In this particular case, the lowest priority group is pointing three-dimensionally away from us, so all I have to do is go from 1 to 2 to 3, and you'll note that that is counterclockwise, hence this stereocenter has an S configuration. Now let's take a look at this tricky-looking molecule here. The priorities of each group are done the same way we did the previous one. Oxygen's the winner, followed by this carboxylic acid group, CO2H, followed by this methyl group, followed by this hydrogen. Now remember the rule. When I go from 1 to 2 to 3 to form either a clockwise or counterclockwise circle, I have to be staring at the molecule in such a way that the lowest priority group is pointing three-dimensionally away from me. Now the way this molecule is drawn, that isn't super obvious, so what I have to do is gain the ability to imagine what I would be seeing if I were an eyeball floating underneath this tripod and staring up the crotch of this three-legged molecule, with this hydrogen pointing away from my eyeball. If I were doing that, you'll note going from 1 to 2 to 3 would indeed be counterclockwise, and thus the stereocenter is S. Now, if that is not clear, please feel free to build a three-dimensional molecular model. Now, I hope you're having a fun time. I know I am. So let's go ahead and tackle the last set down here. Stereocenter is in the middle, stuck to a nitrogen, carbon, carbon, and hydrogen. The winner is the nitrogen. As I break the tie, you'll notice this carbon triple bonded to a nitrogen on the left is higher in priority than the CH3 to the right. And the hydrogen, of course, is the loser. Going from 1 to 2 to 3 looks like counterclockwise, but if I were staring at it from the opposite side of the screen with the lowest priority group pointing three-dimensionally away from me, it would be clockwise. Thus, this is an R stereocenter. As I reason my way through this molecule to the right, I've got nitrogen being the highest priority group, followed by this carbon triple bond to the nitrogen, followed by this CH3, followed by this hydrogen and back. Because my hydrogen and back is pointing three-dimensionally away from us at the perspective that we have right now, I can go from 1 to 2 to 3 as is, and note that it is counterclockwise. Thus, this molecule is S. Now, the original question asks us, are the following pairs of molecules enantiomers? You'll note that the molecules up here in the upper left-hand corner look exactly the same. That is, they each have a carbon that's bonded to a bromine, a methyl, a CO2H, and an H. Except one of them is S and the other is R. What I want to tell you is this. If I have two molecules that look otherwise identical, but one of them is S and the other is R, then they are enantiomers. Let's look at this set over here. I've got two molecules that both have a carbon in the middle bonded to a hydrogen, an OH, a CO2H, and a methyl. Both of them are bonded to the same four things. You'll also note that both of them have an S configuration. So what does that make them? Are they enantiomers? No, they aren't. Because they have the same configuration, what they are is the exact same molecule, just drawn in two different ways. Thus, if you were to build a three-dimensional model of the molecule shown here to the left and of the molecule shown here to the right, you would notice that you can rotate the molecule at the right in a way that points all four of its substituents in the exact same directions as the four substituents of the molecule at the left. Now, by similar logic we had in the upper left-hand group, you'll notice that this lower left-hand group have two molecules that otherwise look identical, but have opposite letter configurations. One is R and the other is S. Thus, these two molecules are also enantiomers. So what's the take-home? Well, if two otherwise identical molecules have opposite RS configurations, then they're enantiomers. If they have the same RS configurations, then they're the same molecule.